All right, our next speaker and the last speaker for this session is Jing Wang, who will talk about quantifying different environmental effects that cause gas depletion in nearby groups and clusters. So take it away.
Thank you. I'm Jing Wang from Kavli Institute for Astronomy and Astrophysics. Yeah, please. Thank you very much. Thank you very much. I put my email address here, and if you find any of my results interesting, you should check with my website because there are too many 1J in China. Okay, I'm going to talk about the environmental effects and galaxy evolution. Environment is considered one of the major factors that drive galaxy evolution. But as observers, when we talk about environment, what parameters do we use to quantify them? We use filaments, superclusters, voids to describe the large-scale environment. We use group mass, distance to the BCGs to describe group catalog-based environments. We also use the simpler local density of galaxies within distance to the third, fifth, 10th neighbor to describe general environmental densities. These are location-motivated parameters. They tell us where the galaxies are in the universe. And when we use them, what we actually have in mind is the physics behind these parameters related to the locations of the galaxies. They come majorly in two categories. One is the cosmological context of structure formation. And the second is the ongoing effects, which make galaxies more passive, bulge-dominated, and dynamically hot. Today, I'm going to focus specifically on the ongoing effects which make galaxies more passive, more gas-poor. H1 gas is a useful tracer because it is a sensitive probe of environmental perturbations. It is of low density, and it is more extended than the optical disks when the galaxies are not yet passive. And it is also the raw material for forming stars, so its removal preludes the quenching or suppression of star formation rates. And H1 is removed while hydrodynamical and gravitational effects. Two major ones among them are the room pressure stripping and the tidal interaction or stripping. So can we use physically motivated parameters to describe environmental effects instead of using location-motivated environmental parameters? Those location-motivated parameters, they are like a black box. They make different effects. But in order to understand galaxy evolution, we actually need to differentiate the different effects, different mechanisms. And there are existing classical models to describe the room pressure stripping and tidal effects. There's Gauss model to describe room pressure stripping, and the Emma-Green model and the other models to describe tidal stripping. Here I list their equations, and I only slightly modify them so that it's easier to apply them to observables. In their models, for the room pressure stripping model, a galaxy that is moved in a cluster with the velocity will feel the room pressure from the intergroup median. If the relative velocity of the galaxy travel is faster or the intergroup median density is higher, the room pressure is higher. Meanwhile, the gravity of the stars and the gas itself will tend to anchor the gas from the stripping, anchor the gas onto the disk. And in the tidal stripping model, for H1 cloud or clump in the galaxy, it feels the tidal forces from the many perturbing surrounding galaxies. And for any of the perturbing neighbor, if the relative velocity is smaller and the distance is smaller from the perturbed galaxy, the tidal force will be stronger. Meanwhile, the momentum of the H1 cloud within the galaxy due to the circular motion will tend to resist the stripping. So based on these models, we can define three parameters: S, F, and T. S is the strength of these effects at the edge of the optical discs. So they directly tell us how much the star-forming regions, the star-forming disks, feel about these perturbations. F is the fraction of the strippable H1, is where the anchoring force cannot anchor the gas against the stripping. And the T stripping is the time scale for stripping the strippable gas. After the length of the time, the strippable gas is gone. With those given models, it's actually relatively straightforward to define these parameters. The major problem was it was hard to apply them to observables. It's obvious that in order to use these parameters, we need to spatially resolve the gas. We also need to detect the gas fraction down to the very gas poor region in order to trace the whole stripping process or history, right? So that was hard until recently. Until we have these observations with Wallaby, which is conducted as ASCAP. Instead of have integral H1 measurements for each individual galaxies, now we can have H1 images for a very large field of view. Here is H1 image for the Hydra cluster, a 30 square degree field of view in one snapshot. And with FAST, the most sensitive single-dish radio telescope, we are able to push down the detection limit much more easily than before. Okay, so with the data, we're able to select representative samples for our study. We selected Hydra, a massive cluster where the room pressure stripping is expected to be a dominating mechanism. We selected Arizonas, which is the merging super group, a merging group of three group systems where the tidal stripping is expected to be prominent. And we also selected a NGC 4636 group, which is actually a normal group. Because it's normal, the different mechanisms they mix, so it's actually more challenging for our method. It will serve as a test, a final test for our parameters and our methods. Now let's get started. We first need a Hydra cluster to test our room pressure parameters. Here are the results. The highlight is the characterization of weak room pressure stripping effects. With this F parameter, the fraction of strippable H1, we're able to identify room pressure stripping galaxies, the galaxies which have F RPS larger than 10%. So within a class-centric distance of 2.5 times the virial radius, around 1/3 of the galaxies are suffering from some kind of room pressure stripping. And if we limit the distance to 1.5 times the virial radius, then 2/3 of the galaxies are suffering from room pressure stripping. But meanwhile, the room pressure stripping for most of the galaxies are relatively weak. If we subtract the strippable H1 from the total H1 at the moment, most of the galaxies only move slightly in the space of H1 mass as a function of stellar mass. Most of the stripping are quite weak. And meanwhile, the stripping for many of the galaxies tend to last long. We do this experiment. We put the observed H1 image of the galaxies at a different cluster-centric distance because the ICM density rises toward the cluster center because there is a slight acceleration as galaxies inflow, so room pressure will become stronger as it moves toward the cluster center. So we can derive the fraction of strippable H1 at these different distances with the observed H1 image. We define dx as well, the F RPS equals x, so that the difference between the actually observed distance and d0.1 is a measure for stripping timescale of stripping the strippable H1. And the d0.1 minus d0.75 is a measure of the timescale for stripping most of the existing H1. It's a depletion timescale. So with these measurements, we found that for a large fraction of the galaxies suffering from round pressure stripping, the depletion time is going to last from several hundred million years to 1 gigayear. It lasts quite long. It's very different from our previous impression from nearby selected target surveys where round pressure usually tends to be strong and quick. So together, they put together, they give us an impression the weak round pressure stripping is very similar to the strangulation mechanism. But the classical strangulation mechanism is for removing the hard CGM, which serves as a reservoir of gas accretion. But here, round pressure stripping, it slowly removes the outer lying H1 disk with the reservoir of H1 that's for flowing into the inner star-forming disk to fill the star formation there. Okay. Now we move to the PS-dominated Arizona's supergroup. And we found that the highlight of the result is for low mass galaxies with stellar mass below 10 to the 9 stellar mass. We found that with the stronger tidal forces at the edge of the optical disks, the size ratio of the H1 disk over the optical size ratio tended to drop when the tidal stripping becomes stronger. And such an effect is much more significant for the low mass galaxies than for the high mass galaxies. So H1 shrinks due to the tidal stripping. Meanwhile, we also look into the color. The central color of the low mass galaxies reddens in response to stronger tidal stripping. It becomes more passive. And the color gradients become more negative as a function of stronger tidal stripping. So the central region reddens in a much more extreme way than the outer regions. The center of the galaxies reddens or quenches inside out. So you may notice that the shrinking of the H1 disk and the quenching of star formation happens in opposite radial directions. It suggests that the response of star formation to the removal of the outlying H1 disk is actually more complex, probably more complex than we thought. And now let's move to the more complex and also more normal intermediate size group, NGC 4636. Because it is more challenging, we can put a lot of telescopes to it. We observe it with ASCAP and FAST. We also obtained AMA images for CO images for 20 galaxies. We also observe the H-alpha narrowband with 5 dark nights and with dark energy camera. And with the fraction of strippable gas, we were able to identify that half of the galaxies is suffering from tidal stripping and more than 2/3 of galaxies suffering from round pressure stripping. If taking them together, 80% of galaxies are suffering from at least one type of stripping and 41% from both types of stripping. So these two types of environmental mechanisms, they are really widespread and coexistent throughout the group. The question is whether it is fair to put these two type of mechanism parameters together. After all, they are from different models, and there are always systematic uncertainties in observations. Right? So we conducted the following analysis. We again look into the size ratio, the H1 size over the optical size, but this time not only as a function of tidal strength, but also as a function of round pressure strength. And we found anti-correlation. The H1 disks, they shrink in response to both effects, become smaller. But the trend has a relatively large scatter, the correlation relatively weak. But if we select the RPS sample, if we look into the relation with the RPS strength only for the RPS sample, and look into the relation with the tidal strength only for the tidal sample, the correlations become much stronger. So it suggests that our parameters really help us to separate the two effects, to separate relatively each effect dominated subsamples. We were able to break the mixture of different effects. We also look into the color again. For low-mass galaxies, again, we see a reddening of the color in response of stronger tidal effects, tidal strengths. But if we include the non-TS samples, which are those gray dots, the correlation will become much weaker, right? It again suggests that our parameter were able to successfully select a TS-dominated sample. So together, they tend to indicate our parameterization, our separation of the two mechanisms, which are usually mixed, relatively successful. And we were able to quantify how H1 disk shrinks and how the color reddens in response to these two effects separately. So, if so, we may also be able to combine them. We can quantify the total stripping fraction of the strippable gas by taking the relatively higher of the two at a time for one galaxy. And we were able to find that this F stripping show a strong correlation, is a strong relation with the H1 richness and the cluster-centric radius. Gas richer and then the higher F stra, and closer to the cluster center, the higher F stra. With this quantification, we are able to derive the stripping timescale for the strippable gas. We quantify it, we incorporate this timescale by using the differential gas decreasement while galaxies inflow into the cluster with this equation here. On the left side, it says how the H1 richness drops when the galaxy is moving toward the cluster center. The right side of the first term represents the efficiency of stripping, the fraction of strippable gas divided by the time scale. The final term is the depletion rate due to star formation. So that's basically the term when only strangulation is happening. And we use the H1 richest galaxy at each cluster-centric radius to trace this process. We select the gas richest galaxies because they are least affected by detection limit. They are most likely to be the first-time infallers. And the gas richest galaxies at a large radius also tend to be the gas richest galaxies at a smaller radius. And we quantify this T stripping with a very simple mathematical format. So combining the two, we can use MCMC to fit the upper envelope of this galaxy distribution in the gas richness versus cluster-centric radius diagram. And the result of T stripping, the time scale is on the right. The green curve and the area is the shaded area. So beyond the very radius, the stripping time scale for stripping the strippable gas can be longer than Hubble time. But when galaxies move toward the cluster center, it drops to a few tenths million years. And then we combine the T stripping and the F stripping, we can derive the depletion time as galaxies inflow. We quantify it as a function of gas richness upon galaxy inflow. So it is the initial condition of the galaxy when it is prepared to be processed by the cluster or group environment. For relatively gas-rich galaxies, which are above 0 or above 0.5, the depletion time quite constant, roughly 3 gigayears. But if the initial condition is relatively gas full, the depletion time sharply drops. Up to now, I have been talking about stripping and depletion, but actually that is not the whole story. With early data from the fifth survey, we were able to quantify the status of gas in an interacting group. And with FAST telescope, we were uniquely identify a diffuse H1, which has a power spectral scale larger than 30 kiloparsec, quite a large scale, has a relatively high surface density, around 10 to the 20, and is quite turbulent with a velocity dispersion around 40 kilometers per second. Usually the textbook velocity dispersion for H1 in a galaxy is around 10 kilometers per second. So it is really turbulent. And with simple modeling, we were able to show that this diffuse H1 is unlikely to be evaporated or photoionized. Instead, it is more likely to cause gas accretion due to turbulent mixing with the CGM and cause cooling there. This diffuse H1 is shown as the dark blue halo-like thing on the left picture, around the much denser H1 revealed by interferometry WSRT before, shown as the lighter blue color there. So it's a halo-like structure and really widespread. That accounts for around 25% of H1 in the whole system and more than 3/4 of the H1 in the IgM. Okay, so now I come to the summary. We tried to use physical model motivated parameters to quantify the different mechanisms that cause gas depletion in groups and clusters. Up to now, we think this method is quite promising. It helps us better understand how the gas is removed due to different mechanisms. And then our next step probably is to apply the method to more systems to see whether the result persists and to see the variation between different systems. Thank you, and I'm ready to take questions.
Right, Joe.
So I have a couple of comments and a question. One comment is that there's another physical mechanism that I'm not sure that you're including in your picture, and that is that the lower mass galaxies tend to have very bursty star formation. And when they have the burst, that will cause a lot of the gas to be ejected from the central part of the galaxy at least, and that gas becomes much easier to strip. So in addition to just thinking of the galaxy as a static place and applying the tidal and ram pressure stripping to the galaxy without the burst, that's a new effect. Second comment, Sandy Faber and I and a number of other people, Doug Hellinger, have been looking both in Sloan and also in MANGA, the subset, at the radial distribution of specific star formation rate or color as a tracer of that. And we're finding that a very large fraction of the lower mass satellite galaxies have a radial star formation rate that's stronger in the center or bluer color in the center. And I think a natural interpretation of that is that the outer gas is being stripped. So that's data that's, I mean, it's very beautiful, this work that you've described, where we can actually use telescopes, especially the new FAST machine, to actually measure the amount of neutral hydrogen. But this is an indirect measure that I think is interesting. Question, it looked like, maybe I misunderstood, you're finding that some of these satellites actually have a radial star formation rate that seems to be lower in the center and higher in the outskirts, which is the opposite of what we find for the majority of the satellites in the Sloan survey, for example. And I wonder what the explanation for that is.
That's very nice comments. Actually, it helped me better explain our results. Firstly, address your question about the reddening in the center in opposite to your results, to this result of you and Sandy. Actually, for local dwarf irregular galaxies of even lower masses, the star formation behavior is consistent to your sample, where the star formation tended to be concentrated in the center. But for our galaxies, which have the roughly same mass range, is redden from the center. And we think in order to understand this, we need to go back to why the low mass galaxies have the star formation concentrated in the center. And if we look into the possible mechanisms in the literature, not only environmental effects can cause the star formation to concentrate in the center for some of the galaxies, but also the fountain mechanism. There's a paper by Emma Green some time ago suggesting that a fountain tend to move the gas inward for dwarf galaxies, concentrate the gas there. And if there's environmental effects, it will perturb this fountain thing, because which tend to happen in the CGM. And also, the centrally concentrated star formation in dwarf galaxies also explained by the volumetric star formation law a few years ago by Bertonelli's group. That will go to the star forming condition for making the gas, using the gas. And if the environmental perturbation tend to, for example, increase the velocity dispersion, make the gas more stable, it will also change the star formation condition, make it less possible to form stars in the center. So our results tend to suggest that the gas stripping, although it moves gas on the outskirts, but it potentially more significantly affect the star formation condition or star formation filling, the material filling in the center region than on the outer region. That's all for your second comments. For your first comments about the stellar feedback-assisted galaxy environmental gas removal, yes, that's a very good point, which is currently missing in our picture. We think related to that, there's degeneracy between our parameters, F stripping and T stripping. They together actually work well to describe the decreasement of gas fraction while galaxies inflow into the cluster center. But because of the feedback-assisted stripping you talked about, the degeneracy, because of degeneracy there, more of the factor, more of the contribution should be moved to the F stripping instead of T stripping. In other words, it should increase F stripping and also increase the T stripping.
Yeah, just one quick question and then one. So first of all, when the sizes get smaller, do they still lie on the mass H1 mass size relation? That's the first question. The second one is you didn't mention starvation at all, so I was just wondering what role does that play?
The first question, we were only able to resolve a portion of the galaxies in the sample, not all of them. For the resolved ones, indeed, they still lie on the size-mass relation. For the second question, starvation is actually considered in our model as this constant term, which is star forming efficiency across the gas depletion. Thank you.
All right, let's thank the speaker again. And let's thank all the speakers in this session. I think we will break for coffee now, and then we'll come back.
Thank you very much for your comment.
And that is that I noticed that you're seeing significant amount of stripping, both tidal and even ram pressure, beyond the virial radius of the
Cluster.
And I can think of two reasons for that. I wonder if you can discriminate between them. One is splashback. Out to about 1.5 times the virial radius, a lot of those galaxies are splashback. And at least in simulations, you can tell by just looking at their velocities that they're flying out to splashback. They're coming in, they're probably on their first income. And if it's basically, the stripping was actually occurring at higher densities inside the virial